So far, we've seen some sequences which oscillate, that do not converge to any particular thing. And we've also seen some sequences that either increase or decrease in magnitude. And that's what's coming up next. As a matter of fact, when we get to series, one of the requirements for some of those series tests to see if it converges or diverges is to show that the terms in your sequence, they decrease. And in order to establish that, let's come up with some definitions for each one of these. Hey, what's happening to the individual terms of the sequence? In this left-hand picture, we can see that they're getting bigger and bigger and bigger. They're increasing. They might be converging to a particular thing, but still the individual terms are increasing. And what that means is that this second term here is bigger than the first one. It means the third term is bigger than the second one, and so on. So we're going to say a sequence is increasing if the a sub nth term is always less than the a sub n plus 1 term for all values of n that are greater than or equal to 1. Again, that just means that the first term is less than the second term, which is less than the third term, and then so on. So if we were having to demonstrate that this was true, that the terms of our sequence are increasing, what we do is we just try to establish this inequality right here. And you can do that either algebraically, or you can do it with calculus by looking at a derivative. We're going to see that here in a minute. All right, obviously the second picture seems like these terms in the sequence are decreasing. They're probably converging to some particular number, but they're also decreasing in order to get to that particular number. And over here on the left, they were increasing in order to get to that particular number, right? Okay, so what does it mean to be decreasing? So in this case, if I look at the second term, it's less than the first term. The third is less than the second, and so on. So we're going to say that our sequence is decreasing if the a sub nth term is greater than the a sub n plus 1, right? Here our first one was bigger than the second one's bigger than the third, and so on. So notice that in both of these definitions, it says for all n greater than or equal to 1. Sometimes that's not the case. Sometimes your sequence starts to increase first before starting to decrease, and that's okay. As long as at some point it starts to decrease and then continues to decrease the rest of the time. All right, but if your function always increases or always decreases for all values of n greater than or equal to 1, we say that it's monotonic. And we've seen that before, strictly monotonic, always increasing versus always decreasing. All right, let's take a look at a couple of examples here. To wrap this up, example 9, show that the sequence 3 over n plus 5 is decreasing. So I can do this in one of two ways. The first and most straightforward way is to just do it algebraically. We want to show that, let me add a page real quick. We want to show that the terms of our sequence, if it's decreasing, the a sub n term is always greater than the a sub n plus 1. So this is what I want to show. A sub n is always greater than a sub n plus 1. That means that it's decreasing. As n gets bigger and bigger and bigger, the terms are getting smaller and smaller and smaller. So in terms of the one that we have right here, I've got 3 over n plus 5. That is essentially my a sub n term. And then in order to get the n plus 1th term, everywhere there's an n, we just stick n plus 1 in its place. And if this is true, then 3 over n plus 5 has to be bigger than 3 over, here in parentheses, n plus 1 plus 5. I just put it in parentheses just so we can see. Obviously, I just stuck in n plus 1 in there, but it really doesn't do anything. Whenever I go to simplify this down, I'd get rid of the parentheses, of course, and combine up the 1 and the 5 and make that n plus 6. Okay. All right, so far so good. Maybe we can already be able to say that, hey, I'm dividing by a slightly larger number. This thing has to be smaller than that one. Maybe it's not clear to you, though, so what you do is you treat this like a proportion, or you solve it thusly. And since these numbers are all positive, n is always greater than or equal to 1 here. It's always a positive number. Our 3's are positive when I cross multiply there. It does not switch our inequality sign, so this is equivalent to 3 times n plus 6 greater than 3 times n plus 5. Is this still a true statement? Okay, so maybe it's still not obvious. Let's distribute the 3 through there. I have 3n plus 18 is greater than 3n plus 15. And whenever you subtract away your 3n's, you can definitely see a true statement here. We have 18 is greater than 15. In other words, if this inequality is true, it implies that 18 is greater than 15, which, it's always the case. So this right here is enough to establish that the terms in the sequence are decreasing. So that's not the only way to do it. The other way to do it is to treat this as a function. You come up with a function, a continuous function that you can take the derivative of. So you're going to let's say, this 3 over n plus 5 be represented by the continuous function f of x is equal to 3 over x plus 5. And then you take its derivative, x plus 5 to the negative 1 power. So f prime of x is equal to negative 3 times x plus 5 to the negative 2 power times the derivative of the interior, which is a big fat 1. All right, and then just rewrite this as a negative 3 over x plus 5 squared. Okay, so this number is always going to be positive because it's going to be squared, and the top here is always a negative number. So that means that no matter what, this is less than 0. And we only need it to be less than 0 for everything greater than 1, but it's always going to be true here, right? So that means that it's decreasing, right? That's how we've done increasing and decreasing up to this point. So therefore, 3 over n plus 5 has to be decreasing. All right, let's look at another one, just one more of these. We're going to show that, again, n over n plus 1, n squared plus 1 is decreasing. Again, why are we doing this? The reason why we're doing this is because it is a requirement for some of the tests. When we get into our series to show that it's convergent, we have to first be sure that the terms of our sequence are decreasing. So that's what we're doing here. So the first thing, if it's decreasing, again, that means the a sub nth term has to be bigger than the term that comes after it, a sub n plus 1. They have to be getting smaller. So I'm going to see if I can establish the fact that n over n squared plus 1 has to be greater than, everywhere there's an n, put an n plus 1 in its place, over n plus 1. This time the parentheses are important, plus 1. So is this thing true? It's definitely not obvious that it's true at this point. So we've got to do some algebra on it. Going to carry over the n plus 1 on the top, and then expand out the bottom as an n squared plus 2n plus 1, but there's already 1 out here, so I'll combine that up and make it 2. Right. So maybe for the purposes of clarity, I just rewrite this as n over n squared plus 1 greater than n plus 1 over n squared plus 2n plus 2. And now do the same cross multiplication thing that we did before. And once again, everything is positive here. So I have something that is 1 or bigger, adding 1 to it, it's positive. I'm squaring 1, adding 1 to it, squaring something that's bigger than 1 or equal to 1 and adding 1 to it is always positive. These things are always positive, so it's not going to switch our inequality sign. So we're left with n times the quantity n squared plus 2n plus 2. It's got to be greater than, weird looking greater than, that's even weirder. Okay, that's a little bit better. And then that's got to be greater than n plus 1 times n squared plus 1. All right, again, not obvious at all. So distribute n cubed plus 2n squared plus 2n. Is that greater than? And then here I'll have to FOIL this guy as an n cubed plus an n squared, and then plus 1. Well, here's one thing that I can notice. And that's about it. Well, maybe I can combine some like terms. I can bring these things over here to that side of the equation. I'm going to subtract over the n squared, and when I do, That makes just 1n squared on the left-hand side. I'll subtract over this n. That's going to make plus n on the left-hand side. Is that greater than 1? So remember that n is greater than or equal to 1. So for n greater than or equal to 1, I plug at least, at like a worst case scenario, they're both 1s, and then I would get a 2 over here. That's going to be greater than 1, so it checks out. So that inequality checks out for n greater than or equal to 1. All right, so sometimes though this process gets so tedious or next to impossible to establish. So what is our alternative plan? It's to use a derivative. And so let's do that one more time. We want to replace our sequence with a continuous function. And how do I do that? I just take the n's out and put x's in its place. So I've got this continuous function, f of x is equal to an x over x squared plus 1. Let me check to make sure that's correct. Okay. And then if it's decreasing, that means its derivative has to be less than 0. So to take the derivative here, we'll have to use the quotient rule. Fun. Derivative of the top is 1 times the bottom, x squared plus 1, minus the top, x, times the derivative of the bottom, which is 2x, over the denominator squared. You haven't forgotten the quotient rule, have ya? Okay. All right, so now let's clean this thing up. We got an x squared. Distribute your 1 through the parentheses here. X squared plus 1 minus, and then combining those up, I'd have a negative 2x squared, which is equal to a 1 minus x squared, I think, up top. And on the bottom, we have x squared plus 1 quantity squared. Okay, so let's examine this a little bit, shall we? So down here in the bottom, it's being squared, so this, regardless of what we plug in here for x, is always going to be a positive number there. That's always positive. Right. So we just need to concern ourselves with the top. Well, if I have blue, 1 minus x squared being equal to 0, x squared is equal to 1 at x equals plus or minus 1. So it changes at 1. As long as x is greater than or equal to 1, or actually greater than 1, then this thing is going to be less than 0, right? If I stick in, a positive 1 here, it's just a 0 on the top, and then that's not less than 0. But if I stick anything that is bigger than 1, if I stick in a 2, then this is 1 minus 4, which is going to be a negative number over a positive number. It's going to be negative. So I can establish that our derivative is less than 0. It's going to be negative for x is greater than 1, which means that the function is decreasing. If the function is decreasing, we can conclude that our series, not our series, our sequence, which was n over n squared plus 1, must also be decreasing. For n greater than 1. And that's pretty much all we would have to establish. Which brings us then to the end of this lesson. And the goal here, again, was, hey, we have sequences, and overall, not just what is the next term of the sequence, because that's kind of like an algebra versus geometry thing. It's, hey, do the terms of the sequence get closer and closer to some number? Does it converge or does it diverge? That divergent thing could be that it shoots off to either positive or negative infinity, or it could be that the terms in your sequence just oscillate and never settle down to anything.